Very excited to introduce our next speaker, Daniel Mann. He's from TNO Eindhoven, and he studied chemistry at the Julius Maximilians University in Würzburg, where he received his degree cum laude. Afterwards, he performed his PhD work at RWTH in Aachen and DWI Leibniz Institute for Interactive Materials, where he graduated cum laude in 2017. He now works since 2019 at TNO and Brightlands Materials Center as a senior scientist. The floor is yours.
Yeah, thank you very much. Nice that you're all here on this session on sustainability. I want to tell you about one of our developments at TNO Brightlands Materials Center, the SunSmart Thermochromic Smart Window. This one is next. Yeah. So first off, I think we have heard about the challenges that we face, global warming and climate change already a few times today. But just to give you a short introduction, we all know how much energy is consumed by the building sector. 40% of the total energy consumption. We also have large part of the CO2 emissions in the EU. Oh, sorry. But also, we are quite dependent on foreign countries on the energy, so it's very important to reduce our energy consumption. And how can we do that? In buildings, one of the major factors to the energy consumption of a building are windows. We all know that because we're working with glass. But we also have different effects of a window in summer or in winter, which contribute to energy consumption. So we have in summer 60% of the heat gain comes through the window. So we have a major contributor to air conditioning demand. And in winter, the glass actually is the most vulnerable part of the building skin for heat loss. So we have 25% of the heat loss going through windows. And you all know that, but what are the current technologies on the market dealing with these issues? Now we have low E glass. In the Netherlands, we call the current standard HR++, which is a Louis-coated double glazing window, where you have good insulating properties. But in summer, the G value is still pretty high, so you still have quite a high solar heat gain, which is beneficial in winter, but in summer, you know that your room can get quite hot. So to reduce the solar heat gain, you'll know we have solar control glazing with a low G value, so that in summer times, we actually have nice, cool rooms. But the problem is that this G value is also low in winter times. So we are also blocking the solar heat in winter when we actually could use it to heat our buildings, but that's not possible. So to have an optimal solution to have for these changing requirements, we actually also need a window which changes its properties. So we need to have a window which can transmit all the solar heat when we want it and which blocks it when we actually don't want it in our building. And that we can do with smart windows. Now, we already heard a talk before, which was talking about changing the transmission of a window with a certain technology. And with that, we can actually have a perfect window which has good energy efficiency in winter times and in summer times. At TNO, we are also developing such a smart window system. Our technology is based on the thermochromic material. Thermochromic means that it changes its properties at a certain temperature. So it's not by an electricity which you put in, it's not that you turn a switch, but the material intrinsically changes its properties when a certain temperature is reached. What is also important here is that the technology is not based on a change in the visible, so it's not darkening your glass, but it's focused on a change in the infrared, so only in the solar heat part. So it stays completely transparent. It changes its properties intrinsically. So you don't need any special installations. You don't need wiring. You don't need special framing. It's just a material which you put as a coating on your glass or in an interlayer for laminated safety glass. And then you can just regularly integrate it into a normal IGU, and you have the optimum energy efficiency that you want. As I said, you can use this material in different types of glass products. So we actually started with the what you see the demonstrator on my right side, on your left side, which is a coating. So it's a liquid coating that we deposit on glass. And in a final step, we then create the functional material on the coated glass plate. But we then quickly saw that we can diversify the product when we start working with pigments. So we started developing a thermochromic pigment, which we now can integrate in a multitude of different glass products. So we can use that pigment also to integrate it into a coating on glass, which you see here on the top. We can integrate that pigment into a common interlayer for safety glazing, for example PVB, but we can also work with other polymers, which we then use for lamination of safety glass. And we can use this pigment to produce a coating on a retrofit film, for example, a PET film, which you then can retroactively put on your glass, which is already installed in a building. What is very important for the material, because thermochromics and vanadium dioxide has been in scientific literature for quite some time, the performance of the material is very important, and that was very challenging for quite some time. So what you actually want is, you want to have a very transparent material, so that in the visible, there's very limited impact on the transparency. And you want to have a large change in the infrared, so that you also have a proper modulation of your material. Here the most important part of the modulating area is actually in the region between 800 and 1400 nanometers, because that's the part where also the major part of the infrared light is. So by optimizing that region, you can reach very high solar modulation properties. And these are just some of the materials that we have produced, where we can reach visible transmissions of up to 75%, and solar modulations with one of the materials of up to 23%. And you see that it's really exceeding everything else which has been published in literature on these kind of materials before. I said that the most important area is between 800 and 1400 nanometers. That's not only because there the infrared intensity is very high, but it's also because these coated glass plates, or these laminated glass plates, you still need to combine with a low E coated glass, because the material is not impacting the insulation properties of your glass. So you need to have the insulation of the low E coating to get to your best smart window in the end. And you all know, if we have a high-performing low E coating, they block a large part of the infrared light. Especially at high wavelength regions, almost everything is blocked by the low E coating. So that means with the thermochromic material in combination with the low E, you anyway cannot modulate this part anymore. But there are low E coatings on the market which are still very transparent in the region 800 to 1400 nanometers. And these are actually the type of low E coatings that you need to use to combine with the thermochromic coating to get to a perfect IGU. And this is, for example, then a spectra how it would look like if you combine the thermochromic coating with a low E coated glass. This is in that case the E-class series from Saint-Gobain. And here you see the shaded area. That's everything that you can modulate between the cold and the hot state. And in that case, for these kind of windows, you then have a difference in G value between the cold and the hot state of up to 13%. To reach optimum energy efficiency. This is just something on the performance and the optical properties of the material. If you are familiar with vanadium dioxide, you also know that the material itself intrinsically doesn't have the most pleasant coloration. So it's slightly yellowish, brownish, which you see here on the sample on the left side. So we also worked on tailoring the color of the material to get to a more neutral color, and that you can do. For example, this is now with PVB interlayers. There are colored PVB materials available, which you then can tune to compensate or to tailor the color to get to a more neutral coloration, which you see here on the right side, and also in this demonstrator, which really is very transparent and color neutral. And what's very important in that case is that you choose a tailoring of color which only is in the visible part, and you still have your modulation behavior in the infrared that you want to use for the performance of your material. What we also have done, we have produced a demonstrator of 1 square meter size and tested that in real environment in the Netherlands. So this is an installation in Eindhoven in the west facade. And what we did there is we integrated temperature sensors into laminate. So this is also based on laminated glass. We laminated temperature sensors into the glass so that we can monitor the temperature of the glass over a year. And we have a sensor behind the glass so that we can also monitor the transmission in the visible, but also in the infrared, so that we can actually see how the material behaves in real environment. The first thing that we looked at was, does the material perform as we want it to perform? And there we did some calculations from some optical measurements of all the materials that we used in the IGU, and calculated that together with the solar AM 1.5 spectrum to get an impression on what the transmission of our demonstrator IGU in comparison to a reference without the thermochromic material would look like. And then we compared it to the measurements which we did in our demonstrator. And we were very happy with that because it matched very well the obtained spectra with the expected, and also the performance was very similar to what we expected from our lab results. Then what I said, so we monitor the temperature and the transmission over a full day or over a full year. So what you see here on the right or on your left side is actually the change in transmission just at one wavelength over time. And you already see that, yeah, over time, the transmission changes all the currently all the time. So it's very difficult to see if there is a change in properties by just looking at the smart window itself. So we need to have a reference where we compare it with, and that's the purple line which you see here, which is a reference window which we also installed there, and it's exactly the same buildup, only without the thermochromic material. And then by calculating the ratio of transmission between the smart window and the reference window, we can actually see if there is a change in the material. And that's what you see here in the black line. So we first have a steady ratio, which is the cold state. And then when the sunlight hits the window and the window temperature heats up, you see that we have a drop in ratio, which corresponds to a blocking behavior of the smart window. As I said, we are also monitoring temperature. What's quite interesting here is that when you compare the ambient temperature to the glass temperature, already the temperature of the reference glass is about 15 degrees higher at the maximum temperature than the ambient. But we also see that the temperature of our thermochromic glass exceeds that again by something like 10 degrees. So the temperature, since the switch is based on temperature, we also need to consider that the glass temperature will be much higher than the ambient. And with all this data, we can then analyze all the days of a year, what kind of temperatures we have on the outside at the window, but also in what kind of state the material is. Does it switch or doesn't it switch? And then we can make an interpretation. Does the window function as we want it to function? And here we just set an arbitrary value at a cutoff value at 21 degrees, so that you can consider that we say, okay, your inside thermostat is set to 21 degrees. If the ambient temperature is below 21 degrees, then I heat. If the ambient temperature is above 21 degrees, then we cool. It's not always the case like that, but we just to make it simple, we assume something like that. So that means we analyze the material if it switches, and if the ambient temperature went above 21 degrees, then we say, okay, it behaved as we wanted. And if the ambient did not exceed 21 degrees and it did not switch, then we also say it behaved as we wanted. And what you can see here is that especially in summer and winter times, the material already behaves completely as we wanted to behave. In autumn and in spring, we see that there are some days where we have a switching material, but the ambient temperature did not exceed 21 degrees. So if we now change that cutoff to 20 degrees, then you already get rid of most of these light green squares, and it looks like that it's behaving better. So it also depends on the cutoff. But it also looks like that currently with the switching temperature which we have here, which is adjusted to 24, 25 degrees, it's still a little bit too low because we see that the temperature of the glass increases quite a lot. So we also, in the next iteration, we will have a material with an increased switching temperature, which we can very easily adjust by just changing the material in the production phase a little bit. Now a bit of an outlook when the material becomes available and you install that in your house, what kind of impact can you have on your energy consumption? So we did building energy simulations and then compared the energy consumption of a building in the Netherlands with our smart window to the same building with the current standard HR++. And there we see that with the material that we have, we can improve the energy efficiency and get to savings of up to 8.8% with the current material that we have developed. And that means with the current energy prices in the Netherlands that you can save up to 20 euros per square meter glass per year on your energy bill. And to just put that a little bit into balance of the costs of the material, we're currently talking about material costs and application costs of something like 3 to 5 euros per square meter. So there you already have quite a good impact on your energy demand at a very low price of the material. Also, CO2 emissions can be reduced quite significantly with the material. We just made here a calculation for the whole Dutch built environment. If everything would be replaced with that smart window, then you can save up to 5.8 megatons CO2 emissions per year. I said, yeah, we developed this material in our labs, and I showed you some demonstrators that we have made. We are now also currently installing a pilot line in our infrastructure with industrial machinery so that we can coat 1 square meter glass. The pilot line will be ready this summer, and we will have an opening where we also invite industrial partners to have a look at it in 10th of October in Geleen. Furthermore, if you are interested in our materials, you have more questions, then you can ask now. You can also come to our booth, which is just outside, and we can have a chat. So first, I need to acknowledge some funding sources, but then I want to thank you all, and I'm ready for some questions.